Hello everyone, I'm Arnab Kumar Paul, a postdoctoral research associate at the Oak Ridge National Lab in USA. I'm here to talk about my paper titled Efficient Metadata Indexing for HPC Storage Systems. This work was done during my PhD at Virginia Tech in collaboration with Gray. So everyone must have done a search on your local file systems. You would have noticed how the search has become better over the years. This search is done using metadata indexing, which indexes the inode information of files and the extended attributes in a file system. For your local file systems, in such as our laptops, it is much easier to optimize metadata indexing approaches when compared to large-scale storage systems. This is because there arise many challenges when implementing an efficient metadata indexer for large-scale HPC storage systems. First, scaling metadata indexing technology from local file systems to HPC storage systems is difficult. In local file systems, the metadata index must index only 1,000,000 files and thus can be kept in memory. However, in HPC systems, the index is too large to reside in memory. Second, the metadata indexing tool should be able to gather the metadata quickly. The typical speed for file system crawlers is around 1,000 files per second. This translates to 18 to 36 hours of crawling for 100 million files. Now, a large-scale HPC storage system can often contain 1 billion files, which implies crawl time in order of weeks. This is not feasible. The resource requirements for a metadata indexer should also be low, so that it does not interfere with other file system activities. Now, existing HPC storage system metadata indexing tools, such as LazyBase and Grand Unified File Index, require dedicated CPU, memory, and disk hardware, making them expensive and difficult to integrate into the storage system. Also, very importantly, metadata changes must be quickly reindexed to prevent a search from returning inaccurate results. It is difficult to keep the metadata index consistent because collecting metadata changes is often slow. Therefore, there is a need for an efficient and scalable metadata indexing system, which gives rise to Brindexer. Here, I show some sample file management questions and metadata search queries. For example, a storage administrator might want to know which files should be migrated to the secondary storage. To answer the question, the search query might look at the size and the access time attributes for all the files in the system. Similarly, you can look at the other questions. Therefore, the metadata attributes which need to be indexed are shown here. All attributes are typically represented in attribute value pairs that describe the properties of a file. Now, for each POSIX file, there will be at least 10 attributes, as you can see. Therefore, for a large-scale HPC storage system with 1 billion files, there will be a minimum of 10 to the power 10 attribute value pairs. The ability to search this massive dataset of metadata attribute pairs effectively gives rise to metadata indexing. This work primarily targets the Lustre parallel file system. However, the work can be extended to other hierarchical parallel file systems as well. We chose Lustre for our implementation because Lustre is open source and it is widely used. As you can see here, Lustre features as the file system in 4 of the top 10 systems in the latest IO 500 list, which rates systems with the best IO performance. Lustre will also form the largest HPC file system in the world when one of the first exascale systems, Frontier, will be deployed in Oak Ridge National Lab this year. Now let us briefly take a look at the architecture of Lustre. We have Lustre clients that read or write data to the file system. This file system data is stored on one or more object storage targets mounted on an object storage server. Applications access file system data by interacting with these storage servers directly for parallel file access. Metadata servers manage the metadata and the placement of data on the data servers. Metadata servers are responsible for one or more metadata targets. Every Lustre file system must have at least one metadata target. A large file system may require more than one metadata target to store its metadata, and therefore Lustre versions after 2.4 support a distributed namespace. A distributed namespace means metadata can be spread across multiple metadata targets, where MDS0, that is the metadata server 0, and the metadata target 0 act as the root of the namespace. The management server is responsible for storing the configuration information for the entire Lustre file system. And all of these components are connected and managed by an internal high-speed data networking protocol called the Lustre network layer. Here is the overall system design of Brindexer. Brindexer runs on file system clients. It consists of the indexer, the crawler, and the metadata query interface. Now, the indexer and the crawler are responsible for crawling the entire file system, collecting the inode details from the metadata servers, and indexing the file system metadata. The reindexer is part of the indexer and interacts with the metadata changelog to keep track of the metadata changes. Users and applications interact with the metadata query interface provided by Brindexer to query the metadata index database stored on the storage servers. Now, let's see in detail how the indexer works. In order to effectively crawl the file system, partitioning techniques need to be used. Hierarchical partitioning is one of the most common approaches used in state-of-the-art metadata indexing tools. It is based on the storage system's namespace and encapsulates separate parts of the namespace into separate partitions, thus allowing more flexible, finer-grained control of the index. An example of hierarchical partitioning is shown here. The namespace is broken into partitions that represent disjoint subtrees. However, hierarchical partitioning faces an important challenge when the disjoint subtrees are skewed. That is, some trees might have more files than others. There is another approach that is called leveled partitioning, which creates index nodes at a particular level in the storage system tree. An example of leveled partitioning is shown here. In the figure, leveled partitioning is done at level 2. Therefore, the file system namespace is divided into disjoint subtrees from level 2, with index nodes at the root of each subtree. This mitigates the issue of hierarchical partitioning, where some trees might be skewed, which affects the indexing performance. In the leveled approach, all directories up to the index level are indexed at the root of the current level. Another major issue of the hierarchical partitioning is that a crawler should be used even before indexing to partition the file system namespace into subtrees. This requires extra resource consumption, which can be overcome by leveled partitioning when no such crawler is needed before indexing. Therefore, Brindexer uses leveled partitioning. Brindexer also performs the leveled partitioning approach in parallel, where the indexing task can be distributed on multiple clients for fast and scalable indexing. Each client node can be assigned a set of subtrees that independently manages the file system indexes under those subtrees. The input to the indexer is the indexing level, where all the directories at that level need to be indexed. The root directory is responsible to index all the directories above the indexing level. Now, for each indexed directory, a recursive read dir is performed to find all subdirectories. Now, for every subdirectory, A stat call is made to get the files of that directory, and to get the inode information for every file, a new lstat call is performed on the file. Each individual index directory is set to a two-level database sharding approach to keep the database shards to a reasonable size. With this approach, what we do is that within each database in the index node, there are database shards. Each database shard holds the metadata information of one or more subdirectories of the index directory. To find the placement of the metadata information for a file, first, MD5 hashing is done on the parent directory of the file to get the database shard. Next, MD5 hash is done on the index directory to find the database within which the database shard is placed. This two-level sharding is done to maximize the query performance. The number of databases per index node is limited to 64. This number is based on our experiments to measure the time to index and query Brindexer for 1 billion files. Now, one of the major considerations when building an indexer is also to build an efficient reindexer. This is because after the initial metadata indexing is done, regular reindexing needs to be performed so that metadata search queries do not return stale results. The most basic reindexing of the metadata can be performed by running the indexing tool at regular intervals to index the entire file system afresh. This is an approach that many state-of-the-art indexing tools such as Goofy and Borg FS use, which maintain the index in an external database outside the file system. However, as you can imagine, this is a very expensive approach for large file systems where the indexer is within the file system itself. Another approach is to keep track of metadata changes and re-index based on those changes. So in snapshot-based approach, periodic snapshots are taken of the file system metadata by making a copy on write clone of the inode file. Given two snapshots, this approach calculates the difference between those two snapshots and identify the files that have changed during the time interval between the two snapshots. The metadata index crawler can then only crawl over the changed files to reindex them. This is much faster than periodic walks of the entire file system. However, this approach depends on a copy on write file system design. Another method is the changelog based approach, where metadata changes are logged as the changes are occurring on the file system itself. So only the files on which any modification event has occurred needs reindexing. So in Brindexer, we use this changelog based approach to track modified directories. Now let's see how can we do this in a scalable manner. First, let us take a look at the metadata changelog that is logged in Lustre. Each tuple in the changelog represents a Lustre file system event. Every row will have an event ID, type of the file system event, the timestamp and the date stamp of the event occurrence, flags used for masking the event, the target file identifier, the parent file identifier, and the target name which triggered the event. Here it is evident that the parent and the target file identifiers need to be resolved to their original absolute paths before they can be sent to the client. The list of events that are recorded in the Lustre changelog are shown here. Now let's take a look at the different steps involved in the reindexer. So Brindexer's reindexer is a multi-threaded set of processes running on file system clients. One thread is responsible for processing the file system's changelogs gathered from the metadata servers, which are processed in parallel on the clients. A fast and efficient caching mechanism is used to store the mappings of the file identifiers to paths to improve the performance of processing of the changelogs. Another thread maintains a suspect file, which has a collection of all the suspect directories that are the directories which have been modified and need to be reindexed for a particular time period. Now, this suspect file is given as an input to the indexer, which then does a stat call for only those suspect directories that are present in the suspect file. This approach allows us to reduce the tracking load of Brindexer by more than 90%. For evaluating, we use two different kinds of workloads. The first is a flat directory structure with a lot of files per directory. The other workload depicts more of a real-world scenario with lesser number of files per directory and having a lot of subdirectories with a max directory depth of 17. Now, for both the workloads, we test Brindexer from 400,000 files to 22 million files. We use a setup with Lustre file system having 4 MDSs, 3 object storage servers, and 2 clients, resulting in a 4.8 terabyte Lustre store. We compare the performance of indexing in Brindexer with the state-of-the-art tool, that is Goofy. For comparing querying performance, we use Goofy, the default find tool in Lustre, that is LFS find, and Robinhood, which is a state-of-the-art tool in Lustre. First, we compare the efficiency of Brindexer by looking at the flame graphs plotted during indexing. In a flame graph, each box represents a function in the stack. On the y-axis, the depth of the stack is shown, and the x-axis spans the sample population. The width of each box shows the amount of time a system call spends on the CPU. The major observation from the flame graph is that the sysnew lstat call, which is used for getting the file's inode information, is represented as one block in Brindexer, whereas multiple individual stack calls in Goofy. Also, the cumulative width of the boxes for sysnew lstat in Goofy exceeds the width of the box in Brindexer, which means that Goofy spends more time in CPU for retrieving the file inode information. This shows that Brindexer is more effective in using the system call to retrieve inode information than Goofy. We also compare the time taken to index both workloads by Brindexer and Goofy. Goofy performs better than Brindexer for flat directory structure workload. This is because the design of Goofy enables optimization for a directory level of 1, where each directory has a large number of files. However, for a more real-world case in hierarchical directory structure workload, Brindexer outperforms Goofy, and as the number of files increase, it is shown that the maximum difference between Brindexer and Goofy is 69% in the time taken to index for 22 million files. We also evaluate the time taken to run a query and get the results back from the index database. So Goofy performs worse than Brindexer, and it is seen that Brindexer reaches an ideal query performance of the file system itself and improves upon the hardware normalized version of the state-of-the-art Goofy by 91%. We also evaluate the resource utilization of Brindexer and Goofy. The CPU utilization of Brindexer during indexing is lesser than Goofy by 46.6% on clients and around 86% on the MDSSs. This is because of the multiple individual stat calls that Goofy makes to the MDS, as we had shown on the flame graphs. This shows that Brindexer can index the file system by having low resource utilization and without hampering file system activities. To conclude, in this paper, we have presented Brindexer, a metadata indexing tool for large-scale HPC storage systems. It has an in-tree design where it uses a parallel leveled partitioning approach to partition the file system namespace into disjoint subtrees. Brindexer maintains an internal metadata index database, which uses a two-level database sharding technique to increase indexing and querying performance. It also uses a changelog-based approach to reindex the file system. Brindexer, when evaluated on a 4.8 terabyte Lustre storage system, shows that it improves the indexing performance by 69% and the querying performance by 91%, with optimal resource utilization when compared to state-of-the-art Goofy and Robinhood engines. Thank you.